How's it going, physical science? I hope you're having a good Tuesday, or if you're having me on Wednesday, that you're having a good Wednesday and that your Tuesday was good. Um, a little clarification about Monday's virtual sound lab that had to do with animal hearing. There was kind of a lot of back and forth and discussion about what was needed to be put into the table. So I'm going to just clarify that just to make sure that everyone is on the same page. So there's no confusion. Now, the big question when we went down to this table of there was 3 data points that we needed to collect: the total range low value, the total range high value, and then this extreme range low value. What that means is the extreme range low value is the point where you get the greatest reaction out of the animal, or the greatest response out of the animal. So if we look at like the bat, for example, if we take this bat and we find that point where the bat is responding to our sound that we're testing on it. So at 12,000 hertz, we see that the bat is expanding its wings about halfway. I know it's hard to tell in the simulation, but it's about halfway. This would be our total range low value. To find that extreme range low value, we're going to find the point where the bat starts to really change and interact with the sound. So let's find the point where that bat starts to really expand its wings. So not 20,000. So at 45,000, that bat is completely extending its wings. This would be the range, 45,000, that we would fill into our extreme low value. And then the high value is just the point where that animal is no longer responding at all to the sound that we are creating in the lab. So this bat is still responding at 120,000 hertz. So if I go to my table, my total high range would be 120,000 hertz. And we said the low range, I can't remember. Let's find what that low range was just quick so everyone understands. I think it was 12,000. So at 12,000, we get the low range value. So I apologize for that confusion yesterday or on Monday, whatever day it is, depending on whatever day you're watching this video. So I'm going to hit save. And something cool. Apparently it doesn't show it until the whole thing is done. So that's okay. So that's kind of all I have about that. If you still have some questions, Google Meet me, remind me, email me, whatever works. As far as assignments go, for physical science, on Monday, you should have, at the end of the day, you should have completed your research on waves, just kind of getting the introduction into waves material, like what a crest is, what a trough is, that kind of information, and get that turned in. On Tuesday, so today at the end of the day or yesterday at the end of the day, you should have had your sound lab turned in, which we got on Friday. We didn't have a lot of time to do it, but it doesn't really take that long. Remember the part where it has you take notes on like a trough and a crest and an amplitude and what all those different definitions. You don't have to do that part because we did that with your research on waves before. For today, we are going to talk all about light. So if you can, we're kind of change gears here. We're going to move away from mechanical waves like sound, like ocean waves, like longitudinal waves, like compressional waves, like transverse waves. We're going to get into sound or light, and we're going to kind of, again, just refresh those basic ideas of what a wave is. So with this light wave, and we'll wait for my slideshow to open up here. With this light wave, there's a few things that are going to change between a mechanical wave and a light wave. A mechanical wave requires a medium, which I hope you guys have figured out. A medium is a material like solid, liquid, or gas that a mechanical wave has to travel through to move. If you're in space, like if you were in Star Wars and you had a battle in space between a bunch of ships. If you've watched the movies, there's a bunch of sound taking place and a bunch of explosions all over the way. That's not how it works with sound or mechanical waves. If there was a mechanical wave in space, you wouldn't be able to hear it. It wouldn't make a sound because there's no medium for that sound wave to travel through. There is no medium in space, or there's not enough for anything to move around. There's no gas. There's barely any gas. There's barely any solids. There's barely any liquids. It's super spread out. Light is a whole different story. Light can travel through anything with or without a medium. You don't need air for light to travel through. You don't need gas or liquid for light to travel through something. It can travel through empty space, which is why it's different from a mechanical wave. If we look at this image here, we have a white beam of light passing through a glass prism, and a rainbow is coming out. We see the colors of the rainbow. We're going to talk about that, and you guys are going to play with it on Friday in our lab. I'm not going to dig too deep into it right now. But this is what we call one part of the light that exists is visible light, the type that we can see. I'll move this up and out of the way so that you can see my pictures and hopefully it doesn't come back. So visible light, or the visible light spectrum, which is the area or the range of light that humans can see. So any light that we can see as people either come in colors of red, orange, yellow, green, blue, indigo, and violet, or Roy G. Biv. You guys have heard this probably since like third grade. So what we're looking for is with visible light, with our colors, the light that human eye can see. Now, if we're talking about a dog, and just like we were looking at sound waves and what animals can hear different levels of sound, it's the same thing with sight. Just because I can see red light doesn't mean a dog can see red light. It doesn't mean a cat could see blue light. There's different ranges that animals can see. If you think about like insects and specifically like bumblebees can see a color pattern that is above violet, or what we call ultraviolet, which allows them to pick up on different types of flowers because flowers themselves are giving off all these different colors. If you were to go infrared or below red, that is when you can actually see heat. The idea of heat vision, that's what you would see in infrared. So if you had a heat camera at night in like an African documentary and you were trying to pick up on an elephant in the dark, infrared would be how you do that. So the big question is there any other types of light that is visible to the human eye? And I hope you already kind of know the answer to this, but if not, take a second and kind of think about it. The answer is yes, visible light is just one type of the electromagnetic radiation, which makes up all the different types of lights, whether we can see them or not. If we look at the bottom left image, we see a rainbow, and then at the end we see lightning. Those are all types of visible light, but there's so much more going on there. If we shine a like blue light or a UV light on a scorpion, it starts to fluoresce. In the top left, you can see a scorpion that's kind of struggling. You see that fluorescing color. You're shining UV light onto it, and it's creating this glowing kind of pattern. So there are many, many different types of light that exist outside of the light that humans can see. So I'm just going to play this quick kind of video about electromagnetic spectrum, because this is going to be one of the big kind of topics that we have to focus on when we're talking about light. And this will keep coming back, whether you're in chemistry, biology, if you go off to college, tech school, whatever. This is going to keep coming back. You will see this. Kind of a long intro, but that's okay.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light.
Do not require a medium.
EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected, and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
So lots and lots of different types of waves, lots and lots of different uses for those waves. Things that we do every day, like go on our cell phones, watch TV, watch this recording of me talking about waves. So this gets into the electromagnetic radiation. This is the title for like every type of light falls into electromagnetic radiation. If we look at that word, electromagnetic, it comes in two parts. Electro meaning electricity and magnetic meaning magnetism. Light has to do with electricity and magnetics. They're combined, and that's where we get this term electromagnetic radiation. Let's see if I can erase this appropriately. Probably not. Let's see if it follows us to the next slide. So energy that shows wave-like behavior as it travels through space. So light, again, we can't have sound traveling through space. There's no medium. Light is the only type of wave that can travel without a medium. And then let's get rid of this so you can actually see. And hopefully that bar goes away. And I'll move this up here out of the way. All electromagnetic radiation travels at the speed of light. And that's 3.00 times 10 to the 8th power meters per second. So every time, every second that goes by, light travels 3.00 times 10 to the 8th power. To put that into perspective, if you're sitting in a classroom right now and maybe there's some natural light coming in through the window, that light took 8 minutes to go from the sun to you. So the light is already 8 minutes old. It took 8 minutes to travel that distance from the sun to you. To bring it a little bit closer to home, every second at that speed, at the speed of light, that light could travel 7.5 times around the planet in 1 second. So it's moving very quickly. It's, as far as we're aware, there's nothing that can move faster than light. And obviously that writing isn't going to go away. So can I delete it? Can I select it? Nope. Well, I'll get rid of it one way or another. Let's go to, I bet I can't. It's probably just going to stick with us the rest of the time, and that's okay. So what are some types of electromagnetic radiation that you know? Well, obviously, I already gave one away. You've got the dancing skeleton, which, yes, you can do that. You can do that in an X-ray. An X-ray is a type of electromagnetic radiation that can travel through soft tissues like skin, eyeballs, organs, but harder tissues like bone structures, it can't, and that light bounces back and kind of reflects off. You can also get microwaves. Microwaves are an essential part of everyday life. I bet almost every one of you have a microwave in your kitchen. There's 3 microwaves in our lunchroom. Can't cook food without those microwave radiation, that electromagnetic radiation by microwaves. And then one that has probably affected each and every one of us very deeply, hopefully not to the extent of this. This poor child has been left out in the sun extremely long and now has gone through basically a 3rd-degree burn. That right there on his back is a boil full of liquid caused by ultraviolet radiation, which, yes, does damage your skin. Side note, ultraviolet radiation, when it hits your body, it enters your cells and destroys your DNA. So the actual sunburn comes about because your body is trying to protect itself against things like cancer. So it kind of goes into, those cells kind of go into a suicide kind of thing, and they destroy themselves. And that's where that red rash kind of comes from, is your body like saying, hey, we can't have this. Let's get rid of it. So yeah, fun things about a sunburn. So this spectrum, let's get rid of that. There we go. The electromagnetic spectrum. This is just a chart that helps us organize all types of light into different rankings based on, 1, its frequency, and 2, its wavelength. So if we look at this electromagnetic spectrum, we have shorter wavelengths on the right and we have longer wavelengths on the left. Things with longer wavelengths have low frequency. If I look at this, and can I move this and get it out of my way? I bet I can't. What if I go to settings? Nope, I can't get rid of it. Just going to have to deal with it. If I look at that frequency, if I have a low frequency, I am going to have a long wavelength. If I have a high frequency, so like a gamma ray, I have shorter wavelength, which means the distance between each wave is super, 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 super tiny. So all the types of light that we have appear on the electromagnetic spectrum. If we look, the rainbow color Roy G. Biv, that's the visible light that we can see, excuse me. It's a super teeny tiny bit of light. Almost all the light that exists, we can't see with our eye. Our eye is very, very limited on what we can see. So here's just kind of another blown up version of the electromagnetic spectrum. So if you need this for any reason, you can go into Google, type in electromagnetic spectrum, and it'll be there for you. It's just a good idea to have an understanding on like how these are organized. So long radio waves are the longest types of light that we have, and gamma rays are the lowest wavelength of light that we have. Also, they have the highest frequency, gamma rays, and the lowest frequency are radio waves. If we look at the visible light here, we have red. Beneath that, we have infrared. Infra means below red. If we look to the right of our violet or our purples, we have ultraviolet, UV, which stands for above violet. And then we have our X-rays and gamma rays. So this part, we're just going to kind of go back. That kind of talks about light. We're just going to go back and kind of just make sure everyone has a brief understanding of all the different types of waves, just to make sure there's no one like left behind. Just got to make sure we cover this bit a little bit. I will minimize this picture. So wavelength. Main thing we're looking for is we're going from crest to crest, that top to top. You could also go trough to trough with light waves like radio waves. You're talking meters. If you're talking gamma rays, you're talking nanometers or even potentially picometers. So super, 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 super small. As we move from left to right along the magnetic spectrum, so we move away from radio waves towards gamma rays, our wavelength is going to get, shifted there, smaller. We have frequency. So frequency is just how often waves travel past a certain point every second. If there's a lot of waves traveling past a point in a second, that has a higher frequency. If there's not a lot of waves passing a certain point every second, it's a low frequency. And we record this in hertz. So when we think about the sound waves we were talking about on Monday with those animals, we were recording in hertz, Hz. That is talking about the frequency of the wave. If you have a larger frequency, you have more energy and the sound is higher. If you have a low frequency or a low hertz value, it's lower. And the same kind of thing goes along with light. It is the opposite of wavelength. So as we move from left to right, our frequency is getting bigger. The amplitude is just the distance from the middle of your wave to the center, or the resting position to the center. Is not affected by wavelength, is not affected by frequency. It's all about the energy. The more energy you have in a wave, the larger that amplitude is going to be. If you think back to the Slinky demo that I did on Friday, if you didn't get to see that, I apologize. There was one section I forgot. But if you didn't see that, the harder I move the Slinky up and down, the larger that wave height did, that amplitude, that wave height got. So it's all based on energy with amplitude. Let's take a pause right now. You guys have been taking good notes, I'm sure. I'll be checking in. Why don't you go take a mass break, get out of the room for a little bit, and then we can come back in like 5 minutes. So go take a mass break, take a break, and then we'll come back in. So there's a couple properties of light and waves that can occur. And in last week's research of waves, mechanical waves, some of you came across these things. So the first is like reflection. You look in a mirror in the morning, that is a reflection of light. The light is bouncing off of you into the mirror, from the mirror into your eyes. A reflection is when a wave strikes an object and bounces off of it. If you're looking in water, so we have this situation of the moon reflected off of an ocean or a lake. The moon's light is traveling from the moon to the surface of the water back into your eyes. There was a time, very briefly, when it was assumed that the way light worked was your eyes created it. It went to the object and traveled back. And they just kind of figured out that didn't make a whole lot of sense. If you hear an echo down a hallway, same kind of idea. It's a reflection of sound. If we're looking at refraction, one of the other types of properties that sound waves or light waves can have is this bending of light caused by an object or a type of wave traveling through a different medium. So here in this image, you have the human eye, and we're talking about light, and we're looking at a fish. So when you look at the water and you see a fish in a body of water, the fish is always higher than the actual fish. So say you were in an island situation and you were surviving off of whatever you could hunt. If you were throwing a spear at where the fish was in the water based on where you saw it, you're going to miss. Always aim below the object in the water you're going towards and you will hit the object. Because when light changes mediums, so in this case we have air where the human eye is and it's traveling into a liquid, the light actually has to bend and slow down when it makes that change. If we think about sound has to do that. If you were talking in air and have to switch to liquid, you can still kind of hear what's going on above the water, but you can't really tell what's going on. It's kind of a little fuzzy, and you just hear like noises because the sound wave is being changed. It's being slowed down. And the same thing kind of goes if you're going in the opposite direction. So here, like I kind of just talked about, here's that situation. We have a survival hunter trying to get this fish. Think about where he needs to aim. Does he aim right at the fish, or does he aim below the fish, or does he aim above the fish, or to the side? Think about what we just kind of talked about, and hopefully you can answer that question. If not, take a second, pause the video, and kind of remember what I just said about light going through the process of refraction, which causes light to bend, and especially when it switches mediums. So it goes from like air to water. What happens to that light? It slows down. So if I were trying to get this fish so I could eat that day, you're going to want to aim beneath that fish so that you could actually hit the fish. Then we have diffraction, and I swear, guys, we're almost done. I know this is a lot. I'm very proud of all of you for sitting through this, taking good notes. I'm not going to do this very often, but it's a good skill to have. Diffraction is the bending of a wave around an object, causes waves to bend. If you were standing out in the hallway, you could hear me talking to you because of the idea of diffraction. The sound waves in the room are being pushed and forced out of the door, and when that happens, they bend around that object and try to fill that whole space. With light, it's the same thing. If I shut off all the lights in this room and I open the door and let the light out that was outside into the room, that light would try to fill the whole space. It wouldn't just be like one straight beam of light entering the room and everywhere else would be dark. The whole room would lighten up a little bit. You could actually, if you shut off the lights off and you're in Miss Haugen's room, there's the greenhouse in the back of the room. That light, that sunlight, fills the whole room even though all the lights are off. That's the idea of diffraction. When a wave has to go through a narrow opening, it's going to spread out and fill the whole entire space. And then I think this is the last slide. standing waves, a wave pattern where amplitude and wavelength are the same. So if my energy, the height of my wave, is the same as the length of my wave, you get this appearance that the wave is staying in one location, that it's not moving. When it actually is, you just can't see it happening because of the characteristics of the wave. The wavelength and the amplitude are exactly the same. In between these waves, we get these places called nodes. That's where between those standing waves, between the crest and the troughs, that point is always at a resting position. It does not move. It stays the same. That is a node. Sorry, this is the last one. Resonance. Everyone's kind of heard of the idea that you could sing a certain note and break a glass. That is possible. If you sing at the frequency that an object is vibrating at, you can break it. If you didn't know, everything vibrates on its own. The table you're sitting at, the chair you're sitting in, your own body is vibrating. All the atoms in it are constantly buzzing in place. If you were to make a light wave or a sound wave that vibrates at that same amount, it's going to put in a lot of energy and end up shattering that object. Kind of cool. And then there's this little video about, if you want a little extra information, I kind of like the crash course videos. They talk a lot of interesting things about lights and pretty much any kind of science that's out there. And they're kind of entertaining, but they give you a lot of information in a very short amount of time, kind of like what I just did. So I apologize that we had to put all that information into one video. Like I said, take some time, break it up, do what you need to. But please take notes on this. If you didn't, you can always go backwards. No big deal. Remember, I am out till next Wednesday. I'm not going to have you do any more of this until next Wednesday. It's not going to be after we get back until we get into stuff like this. But if you need me for anything, Google Meet, Remind, email. 3 great ways to reach me. During class, I'll be in Google Meets all the time. If you have any questions, please use that resource so I can contact you. If you need to reach me outside of school, send me an email. We can set something up. No problem. I'm all for it. If there's not anything else, I hope to hear from you soon. I hope to be back soon. I hope you have a good rest of your day. If it's Tuesday or Wednesday, whatever, enjoy your week. Bye-bye.